Okay, today we're going to start chapter 5, which is going to be on logarithmic and exponential functions. And we're really going to start first with exponential functions and their graphs, which is something that you've seen before in Algebra 1. Probably you've dealt with exponents. I don't think that you've ever graphed them, but we'll start that today. So the first thing we're going to talk about is what is an exponential function. And an exponential function is a function where the exponent is a variable. So there's an exponent in it, and the exponent is the variable x, okay? So the value of the function, f of x, is a to the x power, okay? Now, that can be anything. So it could be, f of x equals 3 to the x power, f of x equals 10 to the x power. It could be f of x equals negative a half to some x power. Basically, the only thing we're using here to represent a is the base of this function. It's the number that's raised to that x variable, okay? So in this particular slide, we say a to the x power. In all the subsequent slides, we say b to the x. B is the more common variable to use for this. What's interesting and what the limitation is, regardless of the letter that we choose to use for our base, the base always has to be greater than 1, okay? And the base cannot equal 1. And you think about it, if the base equaled 1, let's at least talk about that, right? So f of x equals a to the x power. F of x equals 1 to the x power. Well, it doesn't matter what x is. Whatever I make x, it's always going to equal 1. If x is 0, it's 1. If x is 1, it's 1. If x is 2, 1 squared is still 1. If x is cubed, it's still 1. And so an exponential function has changing outputs, and this is a constant output. So that's why it can't equal 1. So anyway, so again, we have our base a in this example and our exponent x. Now here they do the more traditional where we call it b, we make the base b, okay? This is the way that you see it most often with the variable b. And this graph that's represented here is the graph of b to the x power. Remember, b has to be a number that is greater than 0, and it cannot equal 1. In this particular problem, the left graph is showing you what an exponential function would look like should the number b be a number greater than 1, okay? And so notice that there's 2 set points on every exponential graph. First of all is whenever x is 0, the output is 1. And let's think about that. If I have, f of x equals some number b, right, to the 0 power, right, or it's b to the x, right? So let's say that x is 0. Well, anything to the 0 power is 1. So whenever x is 0 in this type of basic parent function of an exponential function or graph, whenever x is 0, the value of the function is 1. So when my input is 0, the output is 1. And that's a steady, common value that you can pretty much bank on it. Now, these do get shifted and transformed and reflected, and we'll talk about that. But the basic parent function is always going to go through 0, 1. The second thing is that when the exponent or the x value is 1, then it's going to be some base to the first power. Well, that's always going to equal the base itself. So when x is 1, the output is always the base. So whatever my base is, my first value is going to be 1, x of 1 and y of b. So these 2 points are common to every single exponential function. And so then what you're going to do is you'll end up graphing it, and you're going to see that this graph will also have some asymptote that it cannot approach. And you're going to have this curve that's going to approach when b is greater than 1, it's going to approach 0 and not touch it, and then it's going to shoot up, and then it's going to grow very fast. It has changing rates of growth. From here to here, it's not that much growth, but from here to here, the growth is vaster. And so again, the growth, as you go forward closer to infinity, it's going to grow more and more and more. If b happens to be a fraction between 0 and 1, then my graph is going to have the same 0, 1 value, and it's going to have the same 1b value here, but you're going to notice that your graph from left to right is going to be decreasing. Okay, so this is a decreasing function, exponential, or we call it a decay because it's going down. And this one is increasing from left to right, and we call that a growth function. Okay, so you're either going to have exponential growth, it gets bigger as x goes up, or you're going to have an exponential decay where it gets smaller. You want to use, a set of maybe like a t-chart, like it says here, if you have to graph more points. But oftentimes, believe it or not, this may be enough to do your graph. Okay. The domain of exponential functions is always all real numbers, and the range is what's going to be affected by how high or how low the graph is going to go. So if I have to graph some, this is the most basic graph that I'm going to do, and notice again here that b is 2, which means it's greater than 0. So I know that this graph is going to take the generic shape like that. And I know that 0, 1 is 1 point, and 1, 2, 1b is the other. So I know that this graph is going to look like that. Okay. When I come over to this one, b is 3. So I know that when x is 0, y is going to be 1. That's my set point for everyone. It's, again, it's a growth graph, so I know it's going to go upwards to the right. And I have my second point is going to be 1 and the base, which in this case is 3. And so I know that my graph is going to look like that. So again, remember your basic, you have some basic, input, output values, and 0, 1 is always there, and 1b is always there, which in this problem translates to 1, 3. Again, if I need an extra point, I can do 2. I know my output is 3 squared or 9. So I know 2, 9 somewhere up here is my third point. So my graph was a little more narrow than I gave it. Okay, so then I get to the next one. I've got 10 to the x. So I know my b value is 10, and I know that's greater than 0, or greater than 1 rather. So I know it's going to be a growth. I know 0, 1 is 1 point, and I know 1, 10 is another. So 2, 4, 6, 8, 10. And so this one, obviously you start to notice the greater b is, the more pulled or stretched my graph is. It's a vertical stretch, really. It's going to be vertically stretched, it's going to be vertically pulled up. Now I get to the first one where b is between 0 and 1. It's a fraction between 0 and 1, so I know this is going to be a decreasing or exponential decay. Again, I'm still going to have 0, 1 as my ordered pair, and when x is 1, y is going to be a half. And so what you see is, okay, my graph is going to approach this axis like that. Now, if I want to get an idea of how steep it is, I may want to plug in -1 into my equation. So if I do 1 over 2 to the -1 power, remember that's like flipping it, 2 over 1, which is 2. So when x is -1, y is 2. And that gives me a little bit of an idea of what my graph will look like there. Okay, but again, 0, 1 is always a point, and 1b is always a point. And the third one you can get from a t-chart or something like that. So we keep going here. We've got another, b is a quarter, so I know b is between 0 and 1. So I know this graph is going to be a decay graph. And again, I know that 0, 1 is always a point. I know that 1b is always a second point, right? So I've got 1 over a quarter. So when x is 1, y is a quarter. So again, I'm getting very close, very fast to that line. And then I might want to try, obviously, a number to the left to kind of get a little bit better. So I'll do -1. So I'll do 1/4 to the -1 power is 4 over 1 to the first, so it equals 4. So when x is -1, y is 4. So here, and then again, I know it goes that way. So 0, 1, always there. 1b, always there. And then that third point might be helpful. Let's do this last one here. Again, my b value in this problem is 1 over 10. It's between 0 and 1, so I know my graph is going to go downward like that. And so, again, 0, 1 is a point. Again, this one's hard because it's going to be, imagine, 1 and 1/10. Now here I might have to change my grids, I might have to, my scale, instead of being 1, maybe I go by halves or tenths, who knows. But again, it's going to get very close to there. And then, yes, I should probably figure out, like, for example, when x is -1. So 10 to the -1 power is 10 over 1 to the first, which equals 10. So -1, and let's say 10's up there, and that one is very steep. So again, my graph is super steep. So that's the basics of this. Now, when we get to here, right? Okay, so now we're going to start getting to the ones that have some transformations or some changes, okay? And so you're going to see some weird stuff happening, right? So like, for example, here, b is 2, and so we know normally this would be a graph that would look like that. It would be a growth graph. But notice that it's 2, but it's raised to the -x power, which is already kind of strange. So if I were just to rewrite this, right, this would be the same as, I could do 1 over 2 to the x power. And so if I'm trying to come up with some values here, let's say when x is 0, this is going to be 1 over 2 to the 0, which is 1 over 1 or 1. So notice 0, 1 is still a part of this graph, right? Let's keep going. Let me try what happens if x is 1, right? So it's going to be 1 over 2 to the 1 power, which is a half. And so when x is 1, y is a half, so it's here. Well, let's try -1, right? So when I try -1, it's going to be, what is 1 over 2 to the -1 power? Well, that's the same as 2 to the 1 power, which is 2. So what ended up happening is that even though it initially looked like it would be a growth, it ended up being a decay. It's a decreasing function. So when what's being attached to the x is negative, what ends up happening to the graph is that the graph went from growth or decay. But really what the graph did, guys, is the graph reflected, in this case, reflected over the y-axis. That's really what happened. This -x made it a reflection over the y-axis. Remember that the y-axis is this y value. And if I had done 2 to the x, okay, if I had graphed 2 to the x, it would have looked like this, okay? It would have been this red graph, okay? This would have been 2 to the x power. And basically this y-axis, okay, is what I ended up flipping it over, and then it mirrored over on the other side, and so it's reflected over that. So that's one change that you might experience, okay? Now again, a table of values will help you to kind of figure it out, and then eventually you'll kind of memorize it. You could say, okay, well, I'm going to graph 2 to the x, and then I'm going to mirror it over across the y-axis. That's definitely a way you could do it, okay? When I come to number 8, right, I start here and I'm like, all right, instead of 3 to the x power, now I have a -3 to the x power. So when you're doing these, I like to think of these as a -1 times 3 to the x power. This helps you to separate. This here is still your b, okay? Whatever's being raised to the power is your b value. So in this problem, b is 3, okay? So, if I was to graph 3 to the x power, normally, right, I know 0, 1 would be a point and 1, 3 would be 1, and I know it would be a growth, right? So what does that negative do? How does that change 3 to the x? What does it do to this thing? So let's see. Let's do a little table of values and let's observe the change. If x is 0, right, if x is 0, then it's -1 times 3 to the 0, which is -1 times 1. So it's -1. So let me do the original in the red. This is what 3 to the x would be. And then let me see what this would be. So 0, -1 here. And then what if I try positive 1, right? Instead of 1b, let's see what would happen. So it's negative 1 times 3 to the 1 power. That's negative 1 times 3, or negative 3. So 1, negative 3. So I think you can already see what's happened here, okay? I'm going to graph this, but what you notice is this is a reflection of the original graph, 3 to the x, reflection over the x-axis, which is interesting, right? So if the negative is attached to the variable, the exponent, it's a reflection over the y-axis. If the negative is attached to the b part of it, not the exponent, but the number, the b, it's a reflection over the x-axis, okay? And so again, pretty cool little transformation. Again, a table of values will always help you with your graph. However, learning these changes and these reflections and transformations are always a good strategy. It makes it definitely a lot quicker. So now let's look at this chart, which is going to talk about those transformations. So let's talk about the ones we just saw, okay? Notice if the minus is in front of the b, it's a reflection about the x-axis. If the minus is attached to the x, it's a reflection about the y-axis. Those are the two problems that we just did, okay? Now, what other transformations are there? Well, let's look at vertical translations. Now, vertical translations means shifts up and down, okay? So what makes it shift up and down? Anything that's not attached to the b to the x power. So in this case, what we're talking about is adding c goes up c units, and subtracting c goes down c units, okay? So this is very similar to when we did parabolas, okay? Now, what we'll do a horizontal translation? Well, again, horizontal translations are shifts right and left, okay? And so anything that does a horizontal change, okay, a horizontal shift, let me get a better color here. Anything that has to do with a horizontal shift is going to have to do with some change attached to the x value. So if I'm adding c to x, I'm going to shift left c units. Remember that shifts left and right are always opposite as they appear. If I'm subtracting c from x, I'm going to shift to the right c units. Okay, so horizontal translations, just like parabolas, they're opposite what they appear. Vertical are exactly as they appear. Plus means up and minus means down in vertical. Again, we did reflections over the x and y axis. And then we also have our vertical stretches and our shrinking and our horizontal. Again, anything that gets done to the b value, like here, like I'm multiplying c times the b, okay? That's going to be a vertical stretch if c is greater than 1. And if c is between 0 and 1, if it's a fraction like a half or a third, then it's going to be a vertical shrink, okay? And the horizontal stretch or shrink is going to be something that is attached to the x value, okay? And again, if and it's always opposite what you think. So if it's greater than 1, it's a horizontal shrink. If it's between 0 and 1, it's going to be a horizontal stretch. So the horizontal ones are the ones that are very counterintuitive. Everything related to horizontals are opposite what you think they will be, okay, or opposite what the vertical change would be. And again, you can always do tables of values to kind of figure it out. So when I come over to here, I'm looking and I see 3 to the x, okay, exponent minus 2. So I know this minus 2, notice it's not attached to the x, so this is a vertical translation or shift, okay, and it's going to be down 2 units. Now, you could do a table of values and actually plug into this equation and find all of these, but now how I recommend to do it is graph the basic parent function 3 to the x, okay, because you know that 3 to the x is going to be a growth graph. You know that it's going to have 0, 1 as a value and 1b is the other value, right? B is 3 here. So 1, 3. So you know that your basic graph is going to look like this, something like that, right? And you could even be a little more precise here if you wanted. Probably, maybe I should have done this. Let me do this again. 0, 1, 1, 3, and maybe do 2. When 3 squared, right? If x is 2 there, 3 squared is 9, right? So I could go to 2, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, there, okay? Just to kind of get the correct steepness there, okay? So this is 3 to the x power. So if I'm going to graph now the one I was actually given, which is 3 to the x minus 2, I know that these 3 points that I plotted, I'm just going to move them down 2 units each. 2 units, 2 units. And again, I know that this graph has this asymptote here at the x-axis, so my asymptote, I know, is going to also shift down 2 units. And so my new graph is going to look like this. Something like that. I mean, I'm not a great artist, and so that's my shift. I just shift each point down 2 units. My asymptote also shifts down 2 units, and I'm good to go, and there's my graph. Okay, and I don't have to worry about doing a table of values, which can take a lot of time. So again, I come here, I know that 3 to the x, again, looks like this, and that's my basic parent function, okay? Except for we subtracted 2 from x, which means I'm going to have a horizontal shift, and I'm going to go 2 units to the right. Again, it's opposite what I think, so a minus 2 would go to the right. So again, the parent function of 3 to the x would be 0, 1, 1, 3, and we already did, it was 2, 9, right? So it was up here. So this was the parent. Again, this is the 3 to the x graph, okay? But now I'm going 2 units to the right. My asymptote stays in the same place, except each one of these points is going to shift 2 units to the right. And again, I'm going to continue, and my asymptote didn't change, so I'm still going to go along the x-axis. And so this is the graph of 3 to the x minus 2 power. And so again, super simple, not a hard process. Just understanding the shifts will help you. So let's keep going with these shifts. I come over to here. I have 4 to the x minus 2 power. So I know, again, the basic is 4 to the x, which is usually, a graph that looks like that, right? So let me graph 4 to the x power. It's going to be 0, 1, always a point. It's going to be 1, 4. And I'm not even going to bother doing 2 because that's going to take me to 16, and I don't want to go that high. So I know this graph goes something like that, okay? That's the basic parent graph, okay? Actually, let me do it in yellow. That's what I've been doing the parents in, right? Okay, so 0, 1, 1, 4, and again, super steep, and whatever. There is 4 to the x power. Now I look at what happened here, and we subtracted 2 from it. So I know, again, this is another shift right? Horizontal is a shift to the right, 2 units. So I take this point and move it 2, and I take this one and move it 2. And really, that's all I need to do. And there's my graph. This is 4 to the x minus 2 power. Okay? So, again, we keep going. I go to this one. Notice it's 4 to the x is my base. Again, I know what that should look like. So let me graph that one. 0, 1, 1, 2, 3, 4. Do my thing. And that's 4 to the x. Now I look at the transformation, and this plus 3 is not attached to the x. So I know this is going to be a vertical shift, and vertical is always as it seems, so it's going to be 3 units up. So 1, 2, 3 here, and this one goes 1, 2, 3 here. Again, and now my asymptote, which was at the x-axis, is now here at x at y is 1, right? It goes up 1, 2. So my graph looks like that. Okay? And that's my new graph. So this is the graph of 4x plus 3. So it's the red graph, 4 to the x power, just shifted up 3 units. And so from here, we just keep doing the same old. Now, again, you might have a graph that has multiple changes, right? Notice here I have 4 to the negative x and then a minus 3. So 4 to the negative x, right, is going to be a reflection over the y-axis, okay? And I know that this minus 3 is going to be a vertical shift down 3 units. And so you might want to do a table of values and go directly to it, or you might want to just start and do, just shift and do your reflections. For example, you might want to start with graphing 4 to the x power. 4 to the x power would start 0, 1, and 1, 4, right? So that would look something like this, okay? So this would be 4 to the x. If I reflected this, I know that I would reflect over the y-axis, and so my graph would actually look like that. So it'd be the blue graph. And then the last thing I would have to do is shift the blue graph down 3 units. So 1, 2, 3 here, 1, 2, 3 here. And my asymptote would go from the y equals 0 to y equals negative 3, because it'd have to go down 3 units as well. And so technically, I now have my graph. So the black graph is the graph of 4 to the minus x minus 3. The blue graph is just 4 to the minus x. So I could do it in stages. Now, you don't have to give me the red and the blue and the black on a test. Ultimately, the graph I need is the black graph. But it is a way to do it, and it is a way to have everything in one spot as you need it. You can see it and you can see the change and whatever. So it is an option. Now we're going to get to 14, where we're going to start dealing with natural numbers. We're going to deal with e, which e has a particular value. So that's something we're going to start to cover. Now e, as we've talked about, e is a natural number that has a specific value. It's like 2.7, I think 1, and it just keeps going like that. And so it's kind of like pi. It has a value, 3.14 or whatever. So for e, you're going to kind of treat it the same way. So if the base is e, then you're going to have a point at 0, 1 always, and at 1, e. So at 1, you're going to be at e. Well, e is between 2 and 3, so it's somewhere around here. And so your graph is still a normal curve, a normal growth graph, okay? It's just that the b value happens to be e, which has a set value of like 2.7. I can't remember if it's 1 or 4 and whatever. And so that's how you would graph that one. So this is the basic graphing and shifting and translating of these functions. This is what we're going to cover in one day, and then we're going to move on to the other parts of the slideshow and subsequent slides, and I'll put those in a separate video. So this will be video 1 for day 1.